Morning, sir.
Am I audible, ma'am?
Yes, sir.
Yes, ma'am.
Shall we start, sir?
Yes, ma'am. Yes.
Yes, sir. A very good morning to all the faculty members, our eminent speaker, Dr. Amit Kumar Garg, and dear participants. I welcome you all on day 4, session 1 of AICTE ISTE 1 week online refresher program, which is on artificial intelligence and cooperative Noma 5G network. I would like to welcome our eminent speaker, Dr. Amit Kumar Garg, assistant professor from IIT Kota. It's my pleasure to introduce him. Dr. Amit Kumar Garg is an assistant professor in the Department of Electronics and Communication Engineering, Indian Institute of Information Technology, Kota. He obtained his PhD from the Department of Electronics and Communication Engineering at Malviya National Institute of Technology, MNIT Jaipur. He received BE and MTech in ECE from the University of Rajasthan and MNIT Jaipur respectively. His current research interest includes fiber optics and photonics, including smart, flexible, energy efficient, and latency aware optical access networks and high speed gigabit passive optical networks. He also works on the latest information and communication technologies for developing smart cities, building, etc. He has published various peer-reviewed international journal conference paper. He is an active member of SPIE and OSA. He is a recipient of the SPIE Officer Travel Grant to attend the leadership workshop in Munich, Germany. He has been associated with the various international conferences in various capacities such as organizing chair, organizing secretary, convener, editor, etc. As a coordinator, he has organized various sponsored faculty development programs and training programs. A few of them are advanced optical access networks and its role in smart cities, high-speed optical links and photonic devices for the next generation data transmission, etc. I welcome you, sir. Now I would like to invite Dr. Amit Kumar Garg to deliver his talk on advanced optical networks for 5G and beyond. Welcome, sir.
Okay, so thank you, ma'am, for such a brief and nice introduction. And I would also like to thank Professor Garima ma'am for giving me this wonderful opportunity. And she is very cooperative. So basically, I had to deliver my lecture on some another day, but I had some urgent meetings. So basically, I requested ma'am, and then ma'am kindly agreed for that, and she scheduled this lecture today. So right now, I'm giving that lecture. Okay, so thank you, ma'am, Garima ma'am. And I'm just sharing my screen. Yes, so my screen is visible.
Yes, sir, it's visible.
Okay, and my voice is also clear?
Yes, sir.
Yeah. Okay, so basically for this session particularly, I will be talking about the advanced optical networks, basically the advanced optical access networks for 5G and beyond. So basically these are some contents. So I'll just let you know about the introduction or motivation why we are going on this topic. Then I will give some brief introduction about the optical access networks, the networks basically which are responsible for providing the very high speed data transmission services that are required for the 5G applications, definitely. And then I will be talking about some flexible, resilient, and bandwidth scalable optical access network architectures. Then basically for the 5G networks, the latency awareness is also a very big challenge. So I'll be talking on that topic also. Okay, so basically when we see just from the 1980s to 90, or we can say when we are moving ahead of 10 years, then basically we are also moving ahead in one generation. Okay, so in 1980 the 1G technology was matured, then 2G, then 3G, then 4G, and basically in this era, that is 2020, we are working on the 5G technology. Okay, and definitely as we grow, the years will pass, we'll be moving on the technologies will be outdated. Okay, so I'm not talking about 1G, 2G, 3G, 4G, as your topic is 5G. So basically for 5G communication or 5G era, basically we required the massive broadband, that is basically you can say the high bandwidth, that are required. And basically we are also have one need, that is the low latency. So when we are transmitting some data, or you just see, if you are just downloading or surfing something on the YouTube, okay, and if it is taking time, then you are just irritated. Okay, so we are not tolerating that. And as the applications are, the high definition applications or videos are increasing, as you can see, just the 1.5 year past. So basically, due to this COVID, the most of the things have been migrated on the online. Okay, so the requirement for high speed is again increased in this particularly 1.5 year. And there are some particular factors, or you can say the characteristics for the 5G, that is the mobility, the very high data rate, the very high capacity. Basically, we can transmit the lots of information or lots of message significantly. Okay, then basically the transmission must have some kind of reliability, resiliency, and security. So that is also required. And definitely the latency, that must also be low, as we cannot tolerate the high latency or the transmission delays. Okay, and the another factor, that is the long battery life. So basically what does it mean? The whatever we are transmitting, the technology which we are using, that must be the energy efficient. Okay, and the massive number of devices. So if you just see last 10 years ago, then how much of us having the mobile phones or the laptops or computers? And if you're just seeing the case of today, and if you'll see the case of 10 years ago, then basically the number of applications, the devices, the users, these are increasing exponentially. Okay, so basically the 5G networks, in the 5G networks, these characteristics must be there. Okay, and as you have already listened 3-4 days on this topic 5G, but I can say that these 5G applications or the 5G services are not possible without the most important technology, that is the optical fiber technology. Okay, so we need to transmit the data through the optical fiber. And basically the government of India also pushing lots to develop this fiber optic technology. So basically in, I think 2013, the government of India started a project, that is National Fiber Optical Network, so in which almost there are 2.5 lakh gram panchayats of India, and the government tried to connect those gram panchayats with the optical fiber connectivity. So basically this project is still in progress, and hopefully within 1 or 2 years we'll be having the fiber connectivity to most of the gram panchayats, and then to provide the services to most of the villages, as the villagers are also required to use these applications or these services. Otherwise, basically the villagers are moving in the urban areas, or we can say the urbanization is happening, but at the same time the density fluctuations are there, as in the village areas the peoples are less and they are migrating towards the urbanization or cities. And what will happen one day when we'll have the sort of space or limitations or resources, then basically, so we need to develop some kind of technology that also provide the significant facilities in the rural areas. Okay, so I'm moving on this, basically the next generation optical wireless access network. So we can say what basically this optical and wireless, let me just have my pointer. Yeah. So basically when we are talking about this optical, so we can say from some kind of office, that is, let's say this optical line terminal or this OLT, and it is sometimes also called as the central office. Okay, so from the central office we are transmitting the data towards the end user. Okay, and how we can transmit the data? So basically we need to deploy the optical fiber, and let's say at some particular point we are able to deploy the optical fiber, and after that it is very difficult to provide the optical fiber to the buildings or to the table, or you can say to the computer. So basically then we must have some kind of wireless mechanism also. So at the end of this optical fiber we can transmit the data through the wireless. So basically this optical wireless communication is making it happen to have some kind of flexibility, mobility, that we can use, or we can access the services at a very high speed. Okay, so basically in this talk I will be talking about the optical access network. Okay, and as you know, in this 5G technology, basically there are some characteristics, that is the long battery life, or we can say the energy consumption should be low, or there is another challenge, that is the very low latency. So I will be talking on these two factors. Okay, and definitely, or in the meanwhile, I will be also talking about the reliability. So basically, when we are providing the data, or we are providing the internet services to the users, and what happens when at some particular point of time the services are disconnected. So basically, how the architecture is capable to provide the reliability or resiliency against the link failure, or that it may be happen due to the transmitter or the OLT resource failure. Okay, then the energy efficiency is one of the most important factor, and then basically the cost efficiency. So basically, when we have deployed some kind of network, we had some certain capital expenditure. Okay, but at the same time, what is the operational cost? That is again an important factor, and from the service provider point of view, the operational expenditures must also be low. So like when the number of users are not constant, as you can say, as sometimes we are using the internet, sometimes we are not using. So basically the number of users and the traffic load is not constant throughout the clock. Okay, so it is changing, it is fluctuating. So whenever the load is below a certain threshold, then basically can we turn off some of the resources? So in this way we can have lower operational expenditures. Okay, and then also the bandwidth efficiency, as we are not interested to waste the bandwidth. If the users are not there, then why should we be transmitting on the 10G or 100G if someone is demanding only 1G or 2.5G? Okay, so I will be talking on these topics, and then basically there are some mechanism. Let's say when one user want to communicate to the another user. So basically what is happening? So when user is transmitting, so user must have to transmit the data to the central office, and then from the central office the data must be diverted to the destined user. Okay, so in this case basically there is a lot of latency, lot of transmission delays. Okay, so is there any way that we can transmit the data from one user to another user without sending the data to the central office? Okay, so yes, we have. So I will be giving some idea on this topic also. Yeah, so as I've already told you about the energy efficiency, so let's say basically in this present scenario, the traditional energy sources such as the hydrocarbon energy, nuclear or natural gases, fossil fuels provide most of the energy. Okay, but you know that these energy resources are not renewable in the nature. Okay, so suppose day by day the users are increasing, day by day the applications are increasing, then how we can suffice, we can provide the sufficient energy in the distant future? No. So at some day we have sort of energy resources. So that's why the energy efficiency is one of the most important factor. Not only due to save the energy, but also as if we are burning the energy, then it is the energy released in some form of another gases, that is the carbon dioxide or carbon monoxide, and that are creating the global warming, or that are distorting our environmental friendly nature. Okay, so that's why the reduction of energy consumption is one of the most important thing. Okay, so what we can do for this? So basically we can harness the renewable energy resources as much as possible, and for some cases the renewable energy resources may not be applicable, or we cannot use the renewable energy. Then basically we must have to develop some kind of protocols, technology, equipment that must consume very low energy. Okay, so I'm just skipping this slide. Yeah, so now I'm moving on this optical access network. Okay, so let me just give you some idea what is this optical access network. So we are having some kind of central office, and we are having here the fiber connectivity. Okay, and we want to provide the internet services to the n number of users, and let's say these are the users. So it is user 1, user 2, user 3, and so on. Okay, then I will be transmitting the data through this optical fiber. Okay, then at some remote node or mid of the path, we are having some kind of splitter. Okay, that must split the incoming signal into the multiple ports. Okay, and from these ports, the data is transmitted to each of the users. So let's say it is the 1x4 power splitter or optical splitter. Okay, then now it is able to provide the services to the 4 users. Okay, so for the downstream transmission, basically when we are transmitting the data from the central office towards the user end, then we can say it is the downstreaming. Or you can say when you are downloading some data from the YouTube. Okay, or what we can say, we are accessing some data from the server, user is accessing the data, so it is called as the downloading. And when we are uploading some data to the server, then it is called as the upstream transmissions. Okay, so user can also send the data towards this central office or the optical line terminal, then it is called as the upstream transmission. Okay, so for downstream transmission, there is no problem. Simultaneously, the n number of users can access the data. But for the upstream transmission, what happens? Suppose at some particular point of time, this user 1, 2, 3, they are transmitting data simultaneously. Then there will be the overlapping. Okay, so that's why there must be some kind of mechanism to transmit the upstream data, and that is called as the TDMA, time division multiple access. So basically, these users are allotted some kind of slots or time slots, and at that particular time slot, the users are transmitting the data towards the central office. Okay, so when we are using this TDM, or we can say this power splitter, and now it is called as the time division multiplex PON. So we are transmitting the data at only one particular wavelength. Definitely, we can transmit on multiple wavelengths, but when we are transmitting the data at, let's say, the wavelength lambda1, then this lambda1 will be transmitting here, and this optical splitter now will split this signal into 4 parts. Let's say if it is 1x4 power splitter. Okay, so this branch will have lambda1, this branch will have lambda1, this branch will have lambda1, and so on. So now, what are the advantage of this time division multiplex PON? So basically, the advantage is as the only one transmitter can provide services to all these users. Okay, and if we just see the cost perspective, then basically as we are transmitting by using only one transmitter, or one transmitter is required in this case, so basically it is the low cost. And this splitter is also very matured and very cheap. Okay, so to deploy the TDM PON, it is basically it requires very low capital expenditure, and the operational expenses are also very low, and the energy consumption is also low, as there is only one transmitter that is required. Okay, but there are certain challenges for this. So basically, when the signal is splitted into multiple parts, so basically what is happening, the strength of the signal is decreasing or reducing, and this loss, basically you can say the splitting loss of this splitter, that is given by approximately 3.5 log of 2n. So let's say for this n4, these losses are approximately 7 dB. Okay, ideally, basically when there is no other loss than this splitting loss, then the losses should be 3 log of 2n. So for 2 ports, the loss will be 3 dB. 3 dB means the half power. Equally, the power is divided into 2 parts. And similarly, for 1x4, it should be the 6 dB. Okay, it means the power is divided 1 4 1 4 1 4 1 4 to each of the port. But due to some practicality, so basically the losses are somewhat higher. So the losses are approximately 3.5 log of 2n. Okay, and less security. So basically, when we are transmitting the data at lambda1, let's say for user 1, okay, and user 2 or user 3 may not require that data, or if the data is not intended for user 2 or user 3, but at the same time the data is reaching to this user 2 and user 3. So basically, it is providing some kind of less security. Okay, and then the lower effective data rate. So basically, if we just see the Shannon's channel capacity theorem, that is C B log of 2 1 plus S by N. Okay, so as the signal is divided into multiple ports at this point. So the signal to noise ratio at this is decreased or reduced significantly. Okay, and when the signal to noise ratio is decreasing, then the channel's capacity is also decreased. Okay, so we cannot transmit the much higher data rates. Okay, so but as nowadays when we are moving for the higher and higher data rates, then the another technology that is called as the wavelength division multiplexed passive optical network. Okay, so this WDM PON has to be deployed, and basically what happens in this case, so let's say there are 4 users. Okay, ONT or ONU both are same thing. So user 1, let's say it is user 1 and it is user 4. Okay, so for providing the services to the 4 users, we require the 4 number of transmitters at the central office. Okay, so here we require TRX1 to TRX4. So let's say this is transmitting the wavelength lambda 1, lambda 2, lambda 3, and lambda 4. So now these 4 wavelengths are transmitted, and then there is one kind of multiplexer that is need to combine all these wavelengths. So in this fiber, optical fiber, this is the optical fiber. So there are 4 signals, that is lambda 1, lambda 2, lambda 3, and lambda 4. Okay, and at the remote node earlier we were having this optical splitter, but right now we are having the another special kind of component or device that is all that is called as the WDM demux, and sometimes it is the basically the arrayed waveguide grating. Okay, so the purpose of this AWG or WDM demux is to separate out all these wavelengths to different ports. So basically this lambda 1 will be here, lambda 2 will be, let's say, for user 2, lambda 3 will be for user 3, and lambda 4 will be for this user 4. Okay, so now the signal is transmitted at different wavelengths for different users. So basically we are not splitting the data in this case, basically. So signal to noise ratio is not reducing significantly. Okay, so the channel capacity in this particular case is very high. We can transmit the data at the 10 Gbps or even higher data rates. And if we just see, yeah, but if we just see what about the cost. Yeah, so we require in this case 4 transmitters. Okay, so 4 transmitter means we need to have the capital expenditure 4 times. And when we are transmitting the signal by 4 transmitters means the energy consumption is also very high. So these are some challenges. Okay, and now let's say if we are transmitting the data from transmitter 1 for this user 1, and at some particular instant of time, if this transmitter 1 fails, it is not working, then what will happen? So by no means we can provide the services to the user 1. So basically this is very static, not flexible. There is no wavelength sharing possible in this case. Okay, but definitely there are certain advantages as high security, because a separate data is transmitted for separate user. Basically it is high secure, low transmission loss, as there is no distribution of signal. Okay, and as separate wavelength is transmitted, so it provides very high transmission speed. Okay, but sometimes we are not required to transmit, or to have the expenses of this WDM PON. We can compromise in somewhat midway. Then basically there is the another technology that is called as the hybrid, that is the combination of TDM PON and WDM PON. Okay, so this is the hybrid WDM TDM PON. So basically in this case we can have few wavelengths, we can have more users. Okay, so let's say in this case there are 2 remote nodes. Okay, it is remote node 1 and it is remote node 2. So at remote node 1 we are using the AWG, arrayed waveguide grating, or that is this WDM, and at remote node 2 we are using the power splitter. Okay, so let's say we are having 132 users. Okay, and imagine just if we are transmitting it by TDM PON, then 3.5 log of 2, 132. So how much losses will be there? So the losses will be very high, and the signal received by the receiver is not within the acceptable range or within the sensitivity levels. So it will not detect the signal properly. Okay. So now what is the solution? So basically when we have 132 users, so let's say we are just splitting or making 4 groups of 32 users each. Okay. And for 32, 3.5 log of 2, 32, so that is 32 to the power 5. So losses will be approximately 17.5 dB. Some losses of fiber will be there. So let's say the total losses are 20 or 22 or 25. And if we are transmitting the data at 0 dBm or 1 dBm or -1 or -3 dBm, whatever it is, so you'll have approximately -25 to -30 dBm power levels at the receiver. And the receivers are able to detect that level very easily without any problem. Okay. So for this, what we need to do, so let's say we are transmitting 4 wavelengths. So we have 4 transmitter. Lambda 1, 2, 3, 4 wavelengths are transmitted. Then we are having the AWG. So it is just demultiplexing. So lambda 1 is coming here, lambda 2, lambda 3, and lambda 4. And then we have power splitter here, that is 1 cross 32. Power splitter. Okay. So this lambda 1 will be distributed to all these ports. Lambda 4 will be distributed to all these ports. So basically, this lambda 1 is shared by this 32 users. So basically, you can say the losses will be somewhat moderate, the cost will be somewhat moderate, the insertion losses will be somewhat moderate. Okay. And if we talk about, so if you just see the case of pure TDM PON, pure WDM PON, and then hybrid. So for pure TDM PON, the insertion losses are very high, and for WDM PON, these are very low definitely, but we can tolerate with some moderate losses. Then the hybrid PON will be the suitable or better option. Okay. Similarly for the security, as only one wavelength for 132 users, so it is very less secured. 132 wavelengths for 132 users, it is very highly secured, but 4 wavelengths for 132 users, so it is moderately secured. Hello. Yes, am I audible? Hello. Hello.
Yes, sir, you are audible.
Okay, okay, yeah. And my screen is visible now?
Yes, sir, perfectly visible.
Yeah, yeah. Okay, and if we talk about this resource sharing, so basically based on this, the cost or the wavelength requirement also depends. So for pure TDM PON, it is fully flexible. Resource sharing, only one wavelength can serve 132 users. So yes, for this case, and for pure WDM, it is the resource sharing is not there, and for hybrid PON, the resource sharing is moderate, or you can say the partial. Okay, and similarly, we can have the cost and wavelength idea. Yeah. So now let us have some idea about the identification of cost and energy efficient multiplexing technique for long reach PON for different network scenario. Okay. So in this case, so basically this is the case for hybrid WDM TDM PON. I've just considered 2 remote nodes. So remote node 1 and remote node 2. So at remote node 1, the order is 1 cross M, and at remote node 2, the order is 1 cross N. So basically what I mean, we can have the power splitter here, AWG here, AWG here, and sometimes for the hybrid. So basically when both are power splitter, then it means pure TDM. When both are AWG, then basically it is the pure WDM. Okay, but we may also have power splitter, AWG, and AWG, and power splitter. Okay, so these are the 2 cases for the hybrid. Okay, so you'll have some different idea. So basically the order of M and N is considered as 8.4, 16.4, 16.8 and 32.8. Or we can say the total number of supported ONUs are 32, 64, 128 and 256. Okay. And if we just see the cost of power splitter and AWG for different ports, so it is approximately given by this, the cost of AWG is 500 plus 70 log of 2x dollar in dollar basically. Okay, and for power splitter it is 200 plus 50 log of 2x, that is also in dollar, and where this x gives the number of ports. Okay, so for splitter 1x4 the cost is $300, and for AWG it is $640. Similarly for 1x8 350 and then 710 and so on. Okay, so you can see the splitter is cheaper than the AWG. Okay, so now if we are deploying the different remote nodes for different network conditions or the different number of users, then this is the remote node cost for different combinations. Okay, so when we are using this pure TDM technology, that is for 32 users, 64 users, 128 users and 256 users, then basically the cost total or overall cost of the remote node is somewhat varying from the $650 to $800 depending on the number of users. Okay, and when we are using the TDM WDM multiplexing technology, then it is somewhat in the range of this $1,000, and for WDM TDM PON definitely it is approximately same but somewhat higher than this. And when we are migrating towards the pure WDM technology, then the cost is very high. Okay, so cost wise this WDM scenario is not preferable. Pure TDM scenario is preferable, but at the same time basically we are having some different insertion loss. Okay, so for this, let's say there are 3 cases of fiber length. So one is the 20-kilometer fiber, another is the 40-kilometer fiber, and then third one is the 60-kilometer fiber. Okay, and again we are having the different number of users. So that is for 8.4, that is 32 users, 64 users, 128 and 256 and so on. Okay, so when you see the insertion loss for this pure TDM PON, here, wherever you see. Okay, so for pure TDM PON, the insertion losses are very high. And if we are increasing somewhat the fiber length, then also the insertion losses will be increasing. Okay, and as we are migrating towards pure WDM PON, then the insertion losses will be low. Why? Because for the power splitter, the insertion losses are defined by 3.5 log of 2n, wherever for the AWG, the insertion losses are approximately 5 dB. That is constant. Okay. So, and what are the number of required wavelengths for these each scenario? So if you are just deploying the pure TDM PON, then only one wavelength can provide services. Definitely, I'm not saying about the performance, because when we are providing the services to 132 users, then the insertion losses will be very high and the receivers may not be able to detect the signal properly, or it will detect only the noise. Okay, so I'm not commenting here for the performance, but just the required number of wavelengths. So for the pure TDM PON, we require only one wavelength, and as we are migrating towards the hybrid, then for TDM WDM PON, we require the number of wavelengths that are somewhat higher. Okay, and if we are moving towards this pure WDM PON, so then in that case the number of wavelengths will be equal to the number of users. Okay, so let's say we are having this scenario 8.4, so 8 cross 4, that is 32. The number of wavelengths are 32. Then in this particular case 64. In this case it is 256. Okay, that is the 32 into 8. So the number of wavelengths are increasing when we are moving ahead towards the pure WDM PON. Okay, so now which technology should we opt or should we select it? Basically, we want that the less number of wavelengths should be used, as we are interested to reduce the energy consumption as well as the operational cost. Okay, but at the same time, the quality of transmission should be within the acceptable range. Okay, so basically, when we are transmitting the data at different data rates, then the receiver sensitivity will be somewhat different. And for 1 Gbps, the receiver sensitivity will be much better. And we are moving at higher data rates, then the receiver sensitivity may decrease due to the non-linear effects occurring into that fiber. Okay, so when we have the less number of users, okay, and we are transmitting the data at 1 Gbps. So for 20 kilometer fiber, for 40 kilometer fiber, for 60 kilometer fiber, we can deploy the pure TDM PON. Okay, and for pure TDM, only one wavelength is required. And as the number of users are increasing, Okay, so for 64 users, 20 kilometer fiber, no problem. We can deploy the TDM PON, pure TDM, up to 40 kilometer, no problem. But when the fiber length is 60 kilometer, then there will be the higher insertion losses, and that are not within the receiver sensitivity levels. So basically, we need to migrate towards the TDM WDM PON, and in this case, we require the 4 wavelengths. Okay, and similarly for this case, let's say 256 users, and for 60 kilometer, we need to deploy the WDM TDM technology, and here we are requiring the 32 number of wavelengths. Okay, and similarly, we are migrating, let's say at 10 Gbps. We are transmitting the data at 10 Gbps. Okay, so for 32 users, no problem. We can transmit within the pure TDM technology. Okay, but if we are increasing the number of users, so here you can see TDM WDM means here definitely we need to deploy the hybrid technology so that the insertion losses will be lower and the signal received at the receiver are within the receiver sensitivity level. Okay, and we are increasing the fiber length also. So let's say this particular case, when we want to transmit the data for 256 users and for the 60 kilometer fiber transmission length, then we must need to deploy the WDM PON technology. So definitely in this case, we are requiring the 256 number of users. So we cannot reduce the energy in this case. Yes, but definitely when we are transmitting the data for only 20 kilometer and we are deploying this WDM technology, then the number of wavelengths required will be 32. That is much larger than the required value. Okay, so we can provide the services to 32 users only by using the 1 wavelength. Okay, so I'm just skipping this slide. Yeah, and I'm moving to another architecture. Yeah. Basically, this is the adaptive bandwidth mechanism using dual rate OLT for energy efficient WDM TDM PON. So right now, earlier on the earlier slide, I've just discussed about the hybrid PON. Okay, hybrid means the deployment of TDM as well as the WDM. Okay, so now onwards, I will be talking about these hybrid PONs only. WDM TDM or TDM WDM, it doesn't mean. Okay, the both are same things. So basically, dual rate transmission. So what does it mean? So basically, whenever the system is requiring the services at 10 Gbps, then are we able to transmit at 10 Gbps? And let's say at some particular duration, let's say in the midnight or in the early morning hours, the most of the users are not active or these are in the ideal phase. They are not requiring the services, but we cannot stop the services. Okay, maybe some of the users may access these services. Okay, so then can we have the architecture, can we have the system so that we can transmit the data at lower rates also? As you just see, when we are transmitting the data, then for the same VR performance, let's say I'm just talking about 10 to the power minus 9. Okay, So for 10 Gbps, the power requirement will be approximately, let's say, minus 34 dBm. Okay. And for 2.5 Gbps, the power requirement is approximately minus 36 dBm. And for 1 Gbps, the power requirement is minus 38 or somewhat minus 38.25 dBm. Okay. So you can see we can have additional 3 to 4 dB of power when we are transmitting the data at 1 Gbps as compared to the 10 Gbps. Okay, so basically this is the architecture. So let me just move on the architecture. So there are 4 optical distribution networks. I'm just divided the users into 4 groups. So again, 32 users here. Each group is having 32 users. So total 128 users. Okay. So now let's say I want to transmit the data. So the users may demand the data services at 10 Gbps or at 1 Gbps. Okay, so for this, what we need to do? So instead of 4 cross 1 AWG, 4 cross 1 AWG, if we deploy the AWG that is of the order of 8 cross 1, that means we are deploying the 8 transmitters. Okay, so there are 8 transmitters. These are transmitting the wavelength signals at 193.1 terahertz, 193.3 terahertz, 193.5 and 7 terahertz, and 4 wavelengths which are transmitted at 193.9 terahertz, 194.1, 3 and 5 terahertz. Okay, so these 4 wavelengths are transmitted at 1 Gbps. These 4 wavelengths are transmitted at 10 Gbps. Okay, so now what will happen? And there is one enter lever. So what the role of this enter lever? So whenever there is the even multiple of 100 gigahertz frequency, that is, if it is 193.1, then it will pass here. But if it is 193.2, then it will be moving in this direction. Okay, similarly 193.9, it is moving here. But if it is 194.0, then it is moving in this direction. Okay, so the role of this interleaver is just to separate out the even and odd multiple of wavelengths of 100 gigahertz. Okay, so now for these transmission wavelengths, all these frequencies of wavelength signals are appearing here. Okay, and we are using this AWG. So AWG is just multiplexing all these wavelengths and it is transmitting. So 8 wavelengths are appearing here. That is 193.1, 193.3, 193.5, 7. And similarly, the 4 1G wavelengths also 193.9, 194.1, 3, 5 terahertz. Okay. So now these are transmitted in this optical fiber. So this is the fiber. Okay, now at the remote node, let's say it is the remote node 1. We have one demultiplexer, that is the 1 cross 4 AWG, WDM demux. So what it will
Hello, sir, you are not audible.
Hello,
Yes, sir.
Yes, yes, sir.
am I audible?
Yes, sir, you are audible.
So up to what slide I was audible? कब से मेरी आवाज नहीं आ रही है?
The last one was okay. Just last one where we were there, na. Suddenly
So
it was your voice was gone and otherwise everything was fine.
Okay. I was on this slide. So are you listening me right now?
We are not able to see your slide.
Yeah. Okay. Yes. Wait. So now my slide is visible.
Yes, sir. Up to that it was clear.
Okay. And I was on this slide. So have you listened this slide also?
Yes, sir. Yes, sir.
Yeah. Okay. So basically, if we are just talking about this particular group, let me just have my pointer. Yeah. Okay. So this particular group is receiving two wavelengths. So that is one is 193.1 and another is 193.9 wavelength. Okay. So what does it mean? So whenever the 10 Gbps signal is required, then we can just turn off these 1 Gbps 4 transmitters. So the services are provided at 10 Gbps. Okay. And let's say in some particular time instant, we are not having much traffic load, then we can migrate to 1 Gbps. So in that case, this 10 Gbps transmitters will be switched off and these 1 Gbps transmitters will be switched on. So basically in this case, definitely the capital expenditure will be somewhat higher as we need to deploy the 8 transmitters in place of 4. But at the same time, we are reducing the energy consumption. We are reducing the operational expenditures. So that is one of the desirable thing for the 5G transmission or the 5G networks. Okay. And now let's say I'm just explaining on this slide only. So at some particular instant of time, we are transmitting the data at 193.9 wavelength. Okay. At 1 Gbps. And at that some particular instant of time, if this transmitter fails or there may be the failure in this link also, then what will happen? So the services can be continued or migrated on this 193.1 wavelengths, as there are two wavelengths which are reaching to each of the user. Okay, so we are talking about this particular group, then 193.1 and 193.9, two wavelengths are accessible. Okay, so if 193.9 wavelength fails, then the services can be migrated on 193.1 without any service interruption. Okay, and similarly, if we are originally transmitting at 193.1 and if it is failed, then we can transmit the services at 193.9. Definitely, if 10 Gbps services are required and we are transmitting at 1G, then definitely the service quality may be somewhat not as expected, but we can continue the transmission of signal until the recovery of the failed or original transmitter. Okay, so this architecture is basically, you can say, the very energy efficient, operational expenditure efficient, and it is also reliable, or you can say the resilient against the transmitter failure. Okay, and yes, so suppose there is one common signal that needs to be transmitted to all the users. So basically it is called as the broadcasting. Okay, whatever happens on the FM or the TV channels. So basically broadcasting means for all, whether someone is interested or not. Okay, but let's say we want to have some common message to send all the users. Okay, so what we need to do, either we need to transmit the same message again on transmitter 1, transmitter 2, transmitter 3, and transmitter 4. Okay, or what we can do, so let's say we are broadcasting the data at 1 Gbps. Okay, so what we'll do, we'll just tune this 193.9 wavelength. Earlier we are transmitting 193.9, so now we are transmitting on 194.0 terahertz. So now it is the even multiple of 100 gigahertz. So this wavelength will come towards this way, and here it is the 2x4 power splitter. It will just split the wavelength into the 4 parts. Okay, So now 194 terahertz wavelength is available here, it is available here, it is available here, and it is available here. So the common message can be sent from only a single transmitter to all the users available in the network. So again, the broadcasting feature further provide the opportunity to reduce the energy consumption as well as the operational expenditures. Okay, yeah. So I am just moving ahead. Okay, and then basically there is one another architecture. Okay, so if we just see from the service provider point of view, so he or she may not be interested to deploy the full network in the initial stage. Okay, so is there any mechanism we can deploy the network, or we can plan or develop or design the network in such a way that as we grow, we increase our resources? Okay, so yes, it is also possible. So let me just move on this slide. So again, there are 4 modules that are transmitting the wavelength at 10 Gbps. Okay, so that is, you can say this module 1, module 2, module 3, and module 4. Okay, so there is no need to deploy all 4 modules initially. I'm just explaining this slide, then you'll understand how we can deploy the network in the pay as you grow phase or manner. Okay, so basically each module is having 4 transmitters. So let's say this module 1 is having TRX11, TRX12, TRX13, TRX14, and this module 2 having TRX21, 22, 23, 24, and so on. Okay, so this multiplexer is just multiplexing all these 4 wavelengths. So these wavelengths are coming here. Okay, I'm just explaining for this particular path. So lambda 11, 12, 13, and 14, and then these wavelengths are coming to this switch, optical switch. Okay, so this switch may be connected in the cross manner, or it may be in the bar manner. Okay, so either this wavelength can be transmitted on this path or in this path. Okay, so if the phase shift of this switch is 180 degree, then the wavelengths are appearing here. So here there are 4 wavelengths, lambda 11, 12, 13, and 14. Okay, so now again it is the 4x4 power splitter, sorry, AWG. So what this AWG is doing, it is just demultiplexing all these wavelength signals. So lambda 11 will appear here, lambda 12 will appear here, lambda 13 will appear here, and lambda 14 is appear here. Okay, so now you just see. And again, this is, let's say, the optical distribution network 1. This is optical distribution network 2. This is optical distribution network 4. Okay, so now lambda 11 is coming here. Okay, and there is one power combiner, as some signal may come from this path also. I will discuss it later. Okay, so now again we are having only here one wavelength right now if this module is there. Okay, so from this module 1 we can provide the services to this, or to this group of users. Okay, as lambda 11 is coming here, lambda 12 is coming here, lambda 13 is coming here, lambda 14 is coming here. Okay, now as the number of users are increasing, okay, the bandwidth requirement are increasing, and if we are just sort of the bandwidth, then what we can do, we can deploy the another module. That is, now we are moving towards this module 2. So module 2 is transmitting the wavelength, that is TRX21, or the wavelength is lambda 21, lambda 22, lambda 23, and lambda 24. Okay, so now these wavelengths will come here. Sorry, this path. Okay, and as this phase shift of this switch is 180 degrees, so it is appearing here. So now lambda 21, 22, 23, and 24. Okay, so now what this AWG will do? So this lambda 21 will come here, 22 will come here, 23 will come here, and this 24 will come here. Okay, so now each optical distribution network or each group is receiving 2 wavelengths, 10 Gbps each. So up to 20 Gbps data rates can be provided to a particular group. And similarly, if there is a demand of 30 Gbps, 40 Gbps, then definitely we can deploy the module 3 and module 4 also. And when there are 4 modules and fully flashed on, then each group is able to receive 4 wavelengths modulated at 10 Gbps. So at 40 Gbps per group, the data can be transmitted. Okay. Now, basically, this architecture is also having the transmission at 1 Gbps. Okay. So now let's say I'm just opening the 1 Gbps transmission. Yeah. Okay. So let's say the 10 Gbps services are not required at all. Okay. So each module is attached with a 1 Gbps transmitter also. Okay. So it will transmit lambda 1, lambda 2, lambda 3, and lambda 4. So now lambda 1 will come here. Now this is the combiner basically. Okay. So whatever coming, I'm not talking about it. So lambda 1 will come here. And then the phase shift is 180 degrees. So lambda 1 will come here. And this lambda 1 is coming here. Okay. And then lambda 1 can be accessed by all these groups, all these users. Okay. And similarly, lambda 4 is coming here, here, and then here, and then here, and again to this group. Okay. So we can turn off these main modules, 10 Gbps modules. Okay. And we can just turn on these modules. Okay. So we can transmit the data at 1 Gbps also. Okay. And now similarly, you can just correlate it with the resiliency or reliability, as the lambda 1 is also reaching there and other 4 wavelengths are also reaching there. Okay. So in the case or event of some kind of transmitter failure, we can transmit the data by the another free transmitter. Okay. I'm not discussing it as we have sort of time. Okay. And there is another important feature, that is the broadcasting. So do this architecture has the broadcasting capability? Yes, it has. So basically now this transmitter is transmitting again at lambda 1, but basically this WDM drop filter wavelength is now kept as lambda 1. Earlier it was not the case. Okay. So now this wavelength will drop at this port 2. So now it is the splitter. So it is splitting wavelength to lambda 1, lambda 1, lambda 1, lambda 1, 4 ports. So it is coming here, lambda 1. Now due to this 180 degree phase shift, it is moving in this way, moving in this way. Similarly, if we are just talking about this, so it is moving in this way. Okay, you can just see. So each user is now, or each group is now able to detect or receive the wavelength that is lambda 1. So we can broadcast the message whenever we have some common message. Yes, definitely. But in this particular case, the 10 Gbps broadcasting is not possible. And for that, definitely we can deploy this TRX as the 10 Gbps. Okay, so I am not talking on that. Yeah, so this architecture is basically very energy efficient. So up to 50% energy is reduced by this architecture. Yeah, and now I'm moving to the another part. That is basically the latency aware architecture. So what happens to the latency basically? And let's say there are n number of users or k number of users, and this user 1 wanted to send some data for this user 2. Okay. So conventionally what happens? So this user 1 transmit the data towards this central office. Okay. So this transmission is some kind of upstream transmission, as user is transmitting the data towards the central office. Okay. So now in this particular case, the upstream bandwidth will be consumed. The transmitter is required to provide certain power. And now at this OLT, the signal is reprocessed, remodulated, retransmitted towards the destined user. Okay. So it is transmitted in the downstream direction. So now it will again consume the downstream bandwidth also. Okay, so the bandwidth consumption is twice. And you just imagine if this fiber is 20 kilometer or 50 kilometer length, so the signal is transmitting here this 50 kilometer fiber and then again 50 kilometer fiber. So twice of this fiber length it needs to traverse this path. Okay, and for the downstream transmission, the transmitter must have some kind of energy. Okay, so it is consuming the twice of the bandwidth, twice of the energy, you can say, and very high latency. So is there any way that we can just divert that particular signal from mid of the path? And this is called as the inter-ONU communication. So what does it mean, inter-ONU communication? The communication between the ONUs without interfering the central office, direct inter-ONU communication. Okay, so is it possible? So yes. So basically this was one architecture which was proposed by some of the researcher. So basically he introduced some kind of fiber break grating. Okay, so let me just give you some idea about this fiber break grating first, then we'll be explaining this. Okay, so this fiber break grating is nothing but it is the fiber that is have some kind of periodic index variation. Okay, so index variation means lower, higher, lower, higher. So the fiber is exposed to some kind of UV exposure so that the refractive index of the fiber changes periodically. Okay, and there is one wavelength that is reflected, so that is break B, lambda b, so that is to delta n effective. This is the delta, so delta is the grating period and n effective is the effective refractive index of this fiber. Okay, so whenever some signal is transmitted, okay, so let's say lambda 1, lambda 2, lambda 3, three wavelengths are transmitted, and lambda b that is equal to lambda 2. Okay, so if the signal is transmitted these wavelengths, so this lambda 2 will come reflected back, and the remaining wavelengths, that is lambda 1 and lambda 3, will be transmitted. Okay, so this FBG here is working as the filter. It is reflecting a particular wavelength and transmitting the remaining wavelengths. Okay, so now let's say this FBG is having the break wavelength lambda 1 for example lambda 1. Okay, and if this user 1 want to communicate to the user 2 or some other user, then it will transmit the data at lambda 1. Okay, so now lambda 1 wavelength is coming here. Okay, so now due to its break wavelength lambda 1, so this wavelength will be reflected back, so it is not transmitted here, so it is not reaching to this OLT, right? So lambda 1 will be coming here, lambda 1 will be coming here, lambda 1 will be coming here, and so on. So basically now if you just see, the transmission of this wavelength lambda 1 is not happening through this fiber. Okay, so lots of the transmission delay is reducing. Okay, so now but there is one problem in this particular architecture, that is, so basically let's say we have 1 cross 32 users. Okay, 1 cross 32 users. So basically the wavelength will go in this way, and then the wavelength will go in this way. So twice the insertion loss will be there. So can we modify this architecture? Yes, so basically I have modified this architecture. Yeah, so I have just splitted this remote node into 2 parts. Okay, so that is 1 cross m and 1 cross n. So let me just explain with this architecture. Yeah. Yeah. So basically, let's say we have the 2-stage PON architecture. We are having the OLT. So whenever we are transmitting the downstream transmission, so lambda 1, 2, 3, 4 wavelengths are transmitted, and we have different FBGs, fiber break gratings, and that has some particular break wavelengths also. So this FBG is having lambda 9 break wavelength, this is having lambda 5 break wavelength, and this is also having the lambda 5 break wavelength. Okay. So now these four wavelengths lambda 1, 2, 3, 4 are coming here, and as the Bragg wavelength of this FBG is lambda 9, so these wavelengths will go here, okay, without any reflection, right? And as this is the 1x4 power splitter, so these wavelengths are distributed to the 4 ports, and then again there is another fiber Bragg grating, okay, that is having the Bragg wavelength of lambda 5. So these wavelengths are different, so any of the wavelengths will not be reflected back, these are transmitted here. So now each user is receiving 4 wavelengths, that is lambda 1, 2, 3, 4, lambda 1, 2, 3, 4 without any problem. Okay, so this is the normal downstream transmission. Okay, now what happens when we are talking about the upstream transmission and the latency aware inter-ONU communication transmission? Okay, so let's see, we want to have the upstream transmission for this particular architecture. Okay, so now it will transmit the data at lambda 10. So lambda 10 will be coming here, and as it is having the Bragg wavelength lambda 5, so without any problem lambda 10 will come here, lambda 10 will come here, and lambda 10 is reaching here. Okay, so without any problem the upstream transmission is happening successfully. And now let's say this particular ONU wanted to communicate within this group only. Okay, this user is not interested to communicate with this user or this group or another group. Okay, so it will now transmit the data at lambda 5. So lambda 5 wavelength will come here, and now as the Bragg wavelength of this FBG is lambda 5, so it is reflected back. So lambda 5 will coming here, coming here, coming here. So only this group is receiving this wavelength lambda 5. Okay, so one important feature is the security, as the data is not shared with this group. And another is that suppose earlier we were having these remote nodes merged. So let's say in this case it is node merged, then the insertion loss will be according to the 1x16. Okay, so there is a much difference in the insertion loss, and according to the insertion loss, the transmitted power, as the insertion losses are low, the transmitted power
Excuse me, sir, not able to hear you again.
Sir, your voice is not audible.
Okay, so now it is audible.
Yes, sir, now audible.
Yeah.
Sir, PPT is not visible. Kindly
Yeah, I'm
share.
just sharing.
Yes, sir.
So now my voice is audible and slides are visible.
Yes, sir. You can continue.
So मेरी आवाज कब से नहीं आ रही थी? Anyone, please?
Sir, from this slide.
From this slide only?
Yes, sir.
Okay, yeah. Okay, so let me just start again this slide. So we are having the 8 transmitters. Okay, so transmitters are transmitting the wavelength at wavelength 193.1234 up to 193.8 terahertz. And then due to this multiplexer, these are multiplexed and transmitted into the fiber. And at the remote node, there is one demultiplexer, that is 1x8 demultiplexer. So it will just separate out these wavelengths 193.1, 193.2, 193.3 and so on, 193.8. Okay, and now here we are having the 50 gigahertz interleaver. Okay, earlier we were having the 100 gigahertz interleaver. Now in this case, the 50 gigahertz interleaver is there. Okay, so now what it will do? It will just separate out the even and odd multiple of 50 gigahertz wavelengths. Okay, so now even multiple will be transmitted in this way and odd will be diverted in this way. So as 193.1 terahertz is the even multiple of 50 gigahertz, the wavelength will come here. This 193.2 will come here, 193.8 will come here, and so on. So each user is receiving the dedicated wavelength. Okay, now let's say ONU1 want to communicate or want to transmit the upstream data. Okay, so how it is possible? So it will now transmit on 194.7 terahertz wavelength. Again, it is the even multiple of 50 gigahertz. So this wavelength will be transmitted here, and now it will come here and come here. And now due to this circulator, basically it will come here and then detected at the receiver by the OLT. Okay, and now let's say this particular ONU, that is ONU 8, wanted to communicate with the another users. Okay, so then what it will do? It will just tune its wavelength from 195.4 to 195.45. So now it is the odd multiple of 50 gigahertz wavelength. So now this wavelength will be diverted here. It is filtered out here. Okay, so the wavelength is coming here. Now, due to this splitter, the wavelength is splitted into the 8 ports, so 195.45, 195.45, and so on. Okay, so now again, this wavelength is connected to each user. So now each user is able to detect or receive the proper inter-ONU wavelength. So there is no interruption or no interference or no transmission of this inter-ONU signal in the optical fiber. Okay, so in this way we can save the lots of latency or transmission delay. Okay, definitely there is one problem in this architecture, that is the inter-ONU communication for a dedicated user is not possible. As basically, let's say the ONU 8 want to communicate to only ONU 1. It is communicating with ONU 1, but simultaneously the data is reaching to ONU 2, 3, 4, and so on. Okay. Then is there any way, suppose from the central office we want to broadcast the data? Yes, so in this case it is possible. So basically there is one WDM overlay transmitter. So whenever we are transmitting the data by this transmitter, it is just overlaying these wavelengths, okay, with the help of the coarse wavelength division multiplexer. So basically, if I just talk about this WDM or DWDM, DMUX, so it is the DWDM, that is the dense wavelength division multiplexing, and it is the coarse wavelength division multiplexing. Okay, so some particular wavelength, so let's say it is transmitting on lambda dB, so it is the downstream direction and broadcasted wavelength. I'm just denominated. You can refer some another wavelength also. Okay, so now this wavelength is appearing here, and now it is transmitted through this fiber, and again there is the demultiplexer, this CWDM. So this particular wavelength lambda BD, it will be coming here. Okay, now it is coming here to the port of this star coupler or this power splitter. Okay, so now this lambda dB basically, So this wavelength is now splitted again to its all output ports. So each user is also receiving this lambda dB. So now we can say earlier this architecture in terms of downstream and upstream, it was pure WDM architecture. Okay, but now in this case, you can say it is the TDM also and it is the WDM also. Okay, yeah. And for upstream transmission and for the inter-ONU transmission, the transmission remains same. So in this particular case, I have just transmitted the inter-ONU data by this ONU1. So in place of 194.7 terahertz wavelength, now the transmitted wavelength is 194.75 wavelength. Okay, so now it will come here, and the wavelength from here will be diverted in this way, as this wavelength is the odd multiple of 50 gigahertz. So now it is appearing here, and then it is again transmitted to all the ports. Okay, so for this architecture also, the point-to-point inter-ONU communication is not there. Yeah, so this is, you can say, the limitation of this architecture is still I'm just working on. Okay. And these are the energy saving. So I've just considered some scenario or assumptions for different ONEs, how much time one ONU is communicating with the central office or OLT, or some with another ONU as the part of the inter-ONU communication. And for this particular case, very high latency is reduced as the transmission of the signal through the fiber is not there. Okay, so up to 80%, 85% of the latency, the most of the latency that is basically occurring due to the optical fiber, so that is not there. Yes, so it is. And the energy saving also, as the signal is transmitted only from the ONU, it is not processed at the OLT or central office, and it is again not retransmitted as a part of the downstream transmission. Okay, so the energy saving also, that, and basically these energy savings vary depending on the conditions. Okay, how much time the ONU1 is engaged, or it is transmitting, and at what rate it is transmitting, and so on. Yes, so I think now I'm just stopping, and I'm just open to the questions. And if you have any queries, then you can also mail me on this, my mail ID, that is amitgarg.ec@iitgota.ac.in. Yeah, so I'm open to the questions, please.
If you have any query, you can unmute yourself. Dr. Riyaz.
Good morning, sir. This is Mangal Singh from Symbiosis Institute of Technology, Pune. Am I audible now?
Yeah, yes, sure. Good morning. Yes,
sir,
Dr. Yes.
Can you please tell some idea about that optical communication for underwater communication, and whatever the models, channel models you proposed what in that presentation? Can you tell something about how we can start, something with this underwater communication with optical communication?
So basically, if you just elaborate more, some particular application, and what's the scenario exactly for which you want to transmit the data in the underwater. So basically, underwater communication, you can transmit the data through the optical fiber also, and you can also transmit the data through the free space optics also.
Sir, I'm talking about this visible light communication part.
Yes, so visible light communication, you can transmit the data, and there are lots of articles there for the underwater communication. And as you know, if you are not talking about the visible light, and when we are transmitting the data, we are receiving the data from one continent to another continent. Okay, then the fiber is laid down under sea, so it is transmitted there. Yeah.
Okay, sir. Thank you.
Yes. So anyone else?
I think so. There is no more query. Thank you so much, sir.
Thank you, sir.
Okay, thank you, ma'am, and for giving this wonderful opportunity. I hope the participants has enjoyed this talk. And if you have further any queries or questions, then you can mail me. So my mail ID is amitgarg.ec@iitquota.ac.in. So you can always mail me. No problem. Okay, so
sir,
thank you,
sure.
ma'am.
Okay, so sir, thank you, sir. Now all participants are requested, kindly switch on your camera for a group photograph. I request to all the participants, turn on your cameras. Thank you, everyone. The next session will be at 11:30 a.m. Kindly join the session sharply at 11:30. Thank you all. Thank